Computers are amazing at finding files in what looks like a chaotic heap of ones and zeros. Today, we'll be looking at linear search and binary search. In a linear search, the computer checks every item in memory until it finds the file it's looking for. Now, imagine we have an array, a jumbled up array if I might add. Now, imagine we're trying to look for the item 5. In a linear search, the computer would check every single item in the array until it finds item 5. Now, in this case, 5 exists, so after 4 searches, it finds 5. Now, imagine 5 doesn't exist. In that case, it will check until the end of the array, and in this case, once it reaches the end of the array, it notifies me that 5 doesn't exist. Now this brings us to the next question. What is the time complexity of this algorithm? Me circling 5 is, in a way, it's trying to trick you, because when we look at the time complexity of the algorithm, we don't look at that particular instance of using it. Rather, we're trying to find out what's the worst time complexity that we can get out of this algorithm. Well, that happens when the element we're looking for is not in the array. So for instance, let's say we're trying to find item 10 in this array. But 10 doesn't exist, so what does the program do? The computer will check every single item until it reaches the end of the list before coming to the conclusion that 10 doesn't exist. Well, to put that in numeric terms, suppose you have an array of n items. The program will have to check every single item in the list, so you get a time complexity of order of n, as you will be checking every single item in the list. Now let's come to binary search. Binary search is potentially a much faster algorithm than linear search. Reason is, it halves the search space after every check. But for this to work out, the array needs to be sorted. Now, let's use an example to make things clear how binary search works. Now, the binary search, the array must be sorted. So in this case, we have a sorted array here. Suppose we want to find item number 8, for example. What we do in binary search is simply find the middle of the array. So now, in this case, let's say after calculation, the computer finds that the middle of the array is here. Now, the item in this array is 6, so it will compare 6 with the desired item. Right? Obviously, we know that 7 is bigger than 6. As a result of this, it will now check this latter half of the array. So now the array from 6 items becomes 3 items. So from 6 items it becomes 3 items. And now it will check the middle of the array, which happens to be the space where 8 is located at, and 7 is smaller than 8. So then it will check this half of the array. And since this half of the array only has 1 item, which can only be 7, and it checks, and boom, we found the item we are looking for. Now, suppose the item doesn't exist, and let's just say 7 happened to be some other number, right? Then it will notify me that 7 doesn't exist. Now this brings us to the next question. What is the time complexity of binary search? Now let's take this example and try to figure out a way to get and derive the time complexity of the algorithm. Well, we know that the algorithm checks the middle of the array, and in a matter of speaking, partition the array into 2 groups. One that is smaller than the middle and one that is larger. We can approximate that to halving the array. We can approximate that to halving the array size. So in this case it halves it, and in this case, and in the next subsequent search, it will halve it further. If you're able to identify every time a search is being called, the array is being halved, or rather it's being divided by 2. And in the worst case scenario, where the item is found on the last search feasible, is that the array is being halved every subsequent search. After every search. So in this case, after the algorithm checks that 3 is not the file we're looking for, it performs a half. Similarly, it checks 2 before performing another half and finding 1. We can simplify this with the equation 2 times 2 times equals to n, and x is equals to the number of searches. We can simplify this to 2 to the power of x equals to n, basic algorithm, basic exponentials, taking log on both sides. Let's carry on here. We'll get log base of 2x equals to log of 2n, and this will simplify to x equals the log 2n. And since x describes the number of searches made, x is also the order of n, because x items are being processed. Therefore, the time complexity is simplified to log of n. Right, the log of n. Now let's compare binary search and linear search. We know that binary search is much faster than linear search, with a time complexity of order of log of n versus order of n, and log of n is significantly faster. But the downside of binary search is that it requires an ordered array, where linear search you can use it on any kind of array. Perhaps one consideration on which algorithm to use is firstly whether or not they are ordered, and secondly the size of array. Because in a more smaller arrays, the difference between linear search and binary search isn't significant. But when we're looking at bigger arrays, binary search would be better than linear search because of the sheer efficiency. Now let's see how to code out linear search and a binary search algorithm. So let's start with an array first, and I'm gonna jump it up for you. So in a linear search, you're going to check every single element in the array. And if the array is equals to our target element, it's going to print found, and it's going to exit the function, ending the program. Otherwise, it's simply, if the for loop ends and the function is yet to return, it's going to print not found. Alright, and just for the sake of completing the function, I'm just going to write return. Now let's test it out. Taking linear search, we're going to take an array and let's find item 5. Now we run this. If we run this code, it's going to print found. Now let's put in an item that it's not in the array, 10. It's going to print not found. Now let's look at binary search. I'm going to implement a recursive version of binary search, but please be free to implement an iterative version. So in binary search, It's going to check in a low, the element to be found, as well as a low marker and a high marker. The low and high marker basically partition the array. We're going to find the middle of the array. It's going to check if the low marker is less or equals to the high marker. Right, so the moment it hits the high marker, we know that we have reached the end of the list. No, we will know that we didn't find the item, so we're going to print not found, and we're just going to return. Now let's say we do now while we're searching the array, we will find the middle of the array first, the middle partition, and we're going to check if the array in mid is higher, lower, or equals to the item that we want to find. So if we did find it, we just print found and return. Otherwise, it's going to check if it's bigger or less than the desired item. So suppose the middle of the array is bigger than the target item, we have to check the lower half of the array. So now similarly, if the middle of the array is bigger, it's smaller in a target item, you have to check the larger half of the array. Now let's test it out. So let's give myself a sorted list. The starting low index has to be 0 because we are looking at the entire list, and obviously the high marker is the last element of the list, which we can get from length of array minus 1. Now if we were to run this code, say that we have found the item, and let's search for an item that doesn't exist. Let's say 12, right? It will say not found. We have looked at the differences between linear search, binary search, as well as how to implement them. If you have any questions, please leave them down in the comment section below, and thank you for your kind attention. Goodbye.